Hey there. Ready to dive into something you probably take for granted like every single day?
Hmm.
We're talking about handedness, but not just the basic lefty versus righty stuff. We're going deeper into the intricate mechanics of how our brains orchestrate this seemingly simple part of our lives.
And you might be surprised to learn just how much is going on beneath the surface.
Yeah.
Our source for this deep dive is a 1995 research paper, Handedness and the Asymmetric Dynamics of Bimanual Rhythmic Coordination.
Ooh.
It sounds complicated, but trust me, we'll break it down into something you can really grasp.
Okay, so let's start with something you probably already know. Most people are right-handed. But here's where it gets interesting. Handedness isn't perfectly symmetrical.
Right.
What does that even mean?
Well, even within right-handers, there's a whole spectrum of dominance.
Okay.
You might write with your right hand, but find your left hand is stronger when it comes to opening jars or certain sports. This study digs into those subtle asymmetries and what they can tell us about how the brain coordinates movement.
So how did they actually study this? What kind of experiment reveals these hidden dynamics?
They had people swing weighted pendulums, one in each hand.
Okay.
Pretty simple, right? But here's the twist. They had them swing in two distinct rhythms.
Okay.
First, in phase where both hands move together like a mirror image. And then anti-phase, where one swings forward as the other swings back.
Right.
This anti-phase rhythm requires much more complex coordination between the two sides of the brain.
I bet that's harder than it sounds. I'm already picturing myself getting tangled up. Did they find anything surprising when they observed people doing this?
Actually, they did. One of the first things they noticed was that left-handers were less consistent in that anti-phase condition.
Oh, really?
Their movements had more variability, meaning their timing wasn't as precise as right-handers.
So is that like having two left feet but for hands? Does this mean left-handers are less coordinated overall?
Not at all. This finding is actually super intriguing because it points to a possible link between left-handedness and a more flexible brain organization. There's a growing body of research suggesting that in left-handed individuals, both hemispheres of the brain might be more equally involved in various tasks.
You might be wondering what the benefits of this flexibility are.
Yeah.
Well, imagine having to adapt to a new tool or a new skill. A more flexible brain organization could make that process faster and easier.
Right.
That makes sense, like being able to switch between different modes of thinking or problem solving. So a bit of a trade-off. Less precision in that one specific task, but potentially more adaptability in the bigger picture. What was the other surprising finding from the study?
The second surprising finding was about which hand leads the movement, even when it's a challenge to keep the hands out of sync.
Okay.
In that anti-phase rhythm, people consistently led with their preferred hand. So right-handers naturally led with their right and left-handers with their left.
But wait, wouldn't you expect the dominant hand to always want to take over?
Right?
I thought that was the whole point of having a dominant hand.
You'd think so, right? But this discovery suggests that handedness is about more than just one hand being stronger or more skilled. It's really about the brain's intricate system for organizing timing and coordination between the limbs. It challenges our simplistic assumptions about how dominance works, even in tasks we think are super basic.
So we've talked about how handedness isn't as black and white as we might think. It's not just about having a dominant hand. It's this intricate dance of timing and coordination between both hands, orchestrated by our brains.
And the study reveals just how fascinating that dance can be. Remember how they were swinging pendulums in that challenging anti-phase rhythm?
Yeah.
One hand forward as the other swings back.
Yeah.
Well, it turns out that even within that pattern, the preferred hand tends to be the leader, setting the pace for the whole movement.
You mentioned earlier that the researchers used a mathematical model to analyze all this data. I have to admit my eyes usually glaze over when I see complicated equations.
Oh, yeah.
But I'm curious. What can a mathematical model tell us about something as seemingly simple as swinging a pendulum?
You'd be surprised how much we can learn from math, even about everyday movements. In this case, the model helps us understand those tiny but crucial timing differences we were talking about. Imagine you're trying to predict the weather. Even small changes in temperature or wind speed can lead to completely different outcomes. It's kind of like that.
Okay, I'm starting to see how those tiny timing variations between the hands could have a ripple effect on the overall coordination pattern. So it's not just about which hand is stronger, it's about how precisely each hand is hitting its mark in the sequence.
Exactly. And think about it. This goes way beyond just swinging pendulums. Those same principles of timing and coordination are at play when you're doing all sorts of things, playing a musical instrument, typing on a keyboard, playing sports.
Yeah.
It all comes back to how the brain orchestrates this intricate dance between the two sides of the body.
This makes me wonder about my own piano playing. Maybe every time I fumble a chord, it's not just a lack of practice, but a tiny timing glitch between my hands. But let's go back to the study for a minute.
Okay.
I remember you mentioning the concept of phase and how it relates to rhythmic movements. I think that deserves a little more unpacking, don't you?
Absolutely. Phase is a key concept here. To understand it, think about the two pendulums swinging. Phase refers to where each pendulum is in its swing cycle at any given moment. So in the in-phase condition, both pendulums are at the same point in their swing at the same time. Forward together, backward together.
Okay, so it's like synchronized swimming, but for pendulums.
Yeah.
What about the anti-phase condition?
In the anti-phase condition, they are always at opposite points in their swing cycle. So when one is swinging forward, the other is swinging backward. The study found that the preferred hand tends to lead this phase relationship, even when it's harder to maintain.
So even when the task gets more challenging, the brain seems to stick to this preference for the dominant hand to set the pace. But didn't the researchers also find some differences in phase between right-handers and left-handers?
They did. There was greater variation in phase, more timing inconsistencies in left-handed individuals, especially in that tricky anti-phase condition.
So going back to that idea of a more flexible brain, perhaps left-handers are exploring a wider range of timing possibilities, even if it means they're not quite as consistent in this specific task. It's like their internal metronome's a bit more fluid.
That's a great way to put it. And this raises a really fascinating question for future research. Are there cognitive advantages or disadvantages that come with this increased flexibility? It's something to ponder, isn't it?
It definitely is. This whole conversation is making me rethink what I thought I knew about handedness. But there's another interesting finding from the study that I'd love to explore. They looked at not just the timing of the hand movements, but also the spatial position of the pendulums at their furthest point of swing. What did they discover about that?
This is where it gets really interesting because it reveals another layer of asymmetry in how our brains control movement. Imagine those pendulums swinging again. The researchers measured how far each pendulum swung outward, both forward and backward, and what they found was pretty striking.
Okay, so we're not just talking about timing anymore, but how far each hand swings the pendulum out. I'm ready for this next layer of the mystery. What did they find?
They discovered that right-handers tended to swing their right-hand pendulum further out, especially in that anti-phase pattern where the hands are alternating.
So it's not only about the right hand leading the rhythm, it's almost like they're putting more oomph into it, even though the pendulums themselves were identical.
Precisely. This wasn't about physical strength, it was all about how the brain was controlling the movement. And this asymmetry wasn't as pronounced in left-handers. They showed less of a difference between their left and right-hand swings.
So this all circles back to that idea of left-handers having a more balanced or flexible control system, right? Like their brains aren't as locked into favoring one side over the other.
It's certainly a compelling hypothesis, and what's truly remarkable is that they were able to link these observations, the timing differences, the spatial patterns, to a mathematical model that describes the underlying dynamics.
You've mentioned this mathematical model a few times, and I know you're trying to keep things accessible for us non-mathematicians.
Right.
But I'm still curious. Can you give us an analogy to help wrap our heads around what this model is actually doing?
Sure. Think of it like trying to understand how two people walking together might influence each other's pace.
Okay.
They're linked, but not perfectly in sync. One person might naturally take slightly longer strides, and the other might adjust their pace subconsciously. The model is trying to map out those subtle influences, that coupling between the two sides, and how it plays out in the actual movement.
Okay, so it's not just each hand doing its own thing.
Mm-hmm.
There's this constant communication going on between them, a sort of negotiation happening behind the scenes, and that's all shaped by our handedness.
That's a great way to put it, and the model is sophisticated enough to account for those individual variations we see. It allows for some flexibility in how strong that coupling is between the two sides, which could explain why some people are strongly right-handed, others are more ambidextrous, and so on.
This is really making me think about the complexities hidden in even the simplest actions. We started with swinging pendulums, and now we're delving into the fundamental ways our brains control our bodies. What's the big takeaway you hope listeners will walk away with from this deep dive into handedness?
The most important thing to remember is this. Handedness is so much more than just preferring one hand over the other. It reflects the fundamental asymmetry in how our brains are organized, and this influences everything from the timing of our movements to the spatial patterns we create.
It's not just about hands either, right? We've got leg dominance, eye dominance. Our whole body is a symphony of these subtle asymmetries.
Exactly. And they're not flaws or limitations. These asymmetries are actually crucial for efficient movement. They allow us to specialize, to become skilled at incredibly complex tasks that require fine-tuned timing and control.
So the next time you see someone juggling, playing a musical instrument, or even just walking down the street with ease and grace, take a moment to appreciate that incredible dance of symmetry and asymmetry happening in their brain, making it all possible.
And maybe even pay attention to your own handedness. Notice any subtle differences in how your hands move, how they interact with the world. It's a glimpse into the intricate and amazing complexity of your own brain.
Thanks for joining us on this deep dive into handedness. Until next time.